So hello, yes, can you hear me? Thank you. Okay, so good afternoon. So today we continue to talk about the synchronous generator. And so far we have learned about the basic constructions of the structures of the generator, the principles of the generator, the equivalent circuit of the generator, and the testings of generators. And from above, right, lessons, we have known that for a given generator, that we have a basic, right, relationship that is one. So we have the so-called internal generated voltage, which here we use the EA to represent it. That depends on three very important factors. So here K represent actually is a relative, right, coefficient that actually is not always the constant, which may change with the K field currents. The second, right, parameter is the field currents. So here we use the RF represented, represented. And the third factor is the rotor speed. Here we're using the W, Ri represented. K, coefficient of the core coil. This is the generation, internal generated voltage in the generators. So the key issues here is that, so internal generated voltage depends on one, the physical coefficient, which actually related to the inductance of the field coils and armature coils also, and the field current, which is a DC current, which depend, which, right, determine the strength of the magnetic field produced by the coils. And here omega r, which is the angular velocity of the rotors, usually is provided via a mover. We said the engine. The engine may be, right, driven by burning of the gasolines or driven by the another kind of the dynamic, right, energies, such as the hydraulic energies, such as the wind energies, such as the burning of the coils, burning of the cores or whatever. So here the chi coefficient of the core coils, that is a function of the current I, itself. So here is a very brief of the generations of the current, generations of the internal voltage, which can be, right, the relationship between them can be obtained by the open circuit tests. Open circuit test. The second point is that the terminal voltage, which we use in the VT represented, which, right, is the internal generated voltage minus the here is armature currents, times that the armature synchronous impedance, which usually comes from two parts. One is the armature per phase resistance. The other one is the armature synchronous reactance. the okay the armature short circuit tests in okay. So the terminal output voltage here we talking about the per phase terminal voltage and is the internal generated voltage EA minus the armature voltage drops with the armature currents. IE here represents the armature currents also is the loading currents. Okay. So the armature impedance here is the RA plus JXS. Okay, could be determined by the short circuit test in junction with the open circuit test. So these 2 points actually summarize the principles of the synchronous generators. Of course, you should know that the angular velocity rotation speed, omega r here, actually determine the frequencies of the generated currents, while that the field currents, the rotation speed, and the core materials together determine the internal generated voltage. The terminal voltage, of course, depends on 1, the internal generated voltage, 2, the armature impedance, which also is the functions of the frequency, because the reactance here always related to the frequencies. Remember these points, okay? Because for a given generator, that the frequencies is supposed to a constant, so we not show them out. But in your mind, you should know that when talking about reactance, the reactance is a product of the frequency and the inductance. So when talking about reactance, in your mind, you should know that the frequency affects the reactance. Okay. And then the RA here is loading currents. So from these 2 points, you can easily find out that the terminal voltage shows decreasing trends with the increase of the loading currents if the internal generated voltage keeps no change. Okay, that's why in the slide here, the point 1, we have citrus elements. When a generator feeds a varying load, the terminal voltage VD changes as a function of loading currents I. The relationship terminal voltage versus the loading current I is called as the regulation curve. Okay, regulation curve. Generally speaking, increased loading currents leading to a decreasing of the terminal voltage if the internal generated voltage no change. So the 2 formulas we show here reminds that the relationships. Okay, so the change in the voltage between no load means that the I equal to 0. The meaning here. So no load means that the armature current equal to 0. Okay? When this equal to 0, internal voltage, terminal voltage is the same, right? You should understand in these points. And full load means that the loading current is the full load values. Okay. In such a way that no load terminal voltage and full load terminal voltage different. Okay. So the change in the voltage between the no load and full load is described as voltage regulation, defined as follows. Okay, here, so the terminal low load voltage, okay, minus the terminal full load voltage over the terminal full voltage as a percentage, okay, so is the voltage regulations. Okay, so you can realize that, okay, the voltage regulation, okay, which, right, actually the no load one is the internal generated voltage. If it is keeps no change, when there is a full load voltage, full load outputs, the terminal voltage will be the full load one. So this is the different definitions of the voltage regulations. Now, the next slide showing you the general relationships between the terminal voltage and loading current for various types of loadings. We have 3 cases to showing you, okay, that here, generally speaking, an increase of loading currents leads to a decrease of the terminal voltage. Of course, this depends on the loading characteristics. Generally, for a lagging load, that means the power factors is lagging. For example, here, we suppose that we have a loading power factor 0.9 laggings. And full load case, that the terminal voltage be 12 kV outputs with a rating loading currents 1000 amperes at this point. Then if you making the circuit open, that means the loading current be 0. Then the terminal voltage will up to 18 kilovolt. 18 kilovolt. Why at the full load case 12 kilovolt, but it is opened. No load case will be 18 kilovolt. When the current increases, then the terminal voltage decreases along this dash line. Okay, along this dash line. Okay, this is a typical lagging power factor terminal voltage loading current curves. Of course, there is assumption hidden here. That means the internal generated voltage no change, which is 18 kilovolts. That's the meaning of it. Okay. Okay, so here here is full load points. So the armature current 1000 amperes at a terminal voltage 12 right kiloamperes. The difference is 6 kilovolts. This 6 kilovolts is due to the internal voltage drops and flow currents. So you can quickly estimate that for these loadings, naturally from the curves, these curves, you can determine the generator's armature reactance. Armature reactance. Similarly, this is for the lagging power factors. That for if this generator be adjusted for unit power factors, that means pure resistive loadings at the same rating levels. So if it is adjusted, that the full load output voltage be 12 kilovolts with full load current 1000 amperes for utility power factor loadings. Then if you making the circuit open, it has 15 kV terminal voltage, which is the internal generated voltage. So that means if you adjust the field currents, the field currents equal, we say R1, R lagging, R1. Now looking at here, for this case, also is the no load. And so we're looking at the resistive loadings. So if we making these generators generated a terminal voltage 12 kV with a full load current 1000 amperes as above, case 1, then if this generator be opened, we will find that the terminal voltage back to 15 kV, while that the loading current be 0, and you will find that the internal generated voltage be 15 kV, corresponding field currents I2, which should smaller than R1. Should smaller than R1. So this means that if we apply for this one, the internal generated voltage lower than that for case 1. Now similarly for case 3, if it is 0.9 leading load, that means we have a capacitors connected to the terminals of this generator, and making the generator has a full load terminal outputs 12 kV 1000 amperes. Then if it is opened, the terminal voltage you found that also no load, but the EA equal to VT equal to here is less than 12, say not exactly, and with the armature current be 0, and the field currents we say equal to I3, which should smaller than I2. You look that for the same generators, with the same rating terminal voltage and flow currents, if the loading power factor is different, their no-load internal generated voltage will be different. This means that their required field current will be different. For a lagging power factor, that they require a relative larger excitation currents, RF. For a leading power factor loading, there requires a relative smaller excitation current, RF. For the same generator, so we based on this curve, right? These diagrams show you the difference in terms of the excitation of the generator for the same rating outputs, but for different power factors. Okay. So this means that for a given generator, if the loadings level is changing and the loadings power factor is changing, and you would like to keep the terminal voltage the same, you have to automatically adjust the internal generated voltage accordingly. That means you have to adjust the field current RF accordingly. So in practice, we have cycle systems be designed, which by monitoring the terminal output voltage and the terminal loading currents to automatically feed back to the internal control unit, that to control the field currents, therefore to control the internal generated voltage. This kind of devices, and this kind of systems, we call it an automatic voltage regulator. Automatic voltage regulator. Okay. Now you understand what does it mean by the automatic voltage regulators. It is systems that to monitor the generator's terminal output voltage at loading levels. So that feed back this message to an internal control unit to control the excitation currents, the field currents, RA, so that the internal generated voltage can overcome the loading voltage drops, so that terminal voltage be always keeps as a constant. So this kind of the devices, we call it automatic voltage regulator. Okay. So generally, we have two types of the automatic voltage regulators. This depends on the excitations of the generator. Okay, now we go ahead to see what kind of the two types of the automatic voltage regulators for AC generators we used in practice. Okay, for the first one, as you can see, the titles here is the self-excited voltage control unit. Okay, this is the voltage control unit. Because our purpose is that to control the terminal output voltage be relative constant. So here is a flow chart of the circuit. Each line here represents a circuit, The circuit depends on whether it is a DC or AC, has different conductors, Don't confuse it. So self-excited means that the voltage control unit itself, the source actually comes from the generator itself. Because if you want to control the devices requires powers. So where does this power come from? So the power comes from generator cells. This is the self-excited generators. First, for self-excited system itself, for successful excitations, there are three basic points for successful self-excitations, which we will talk in detail in the DC machines in next chapters. But here I would like to remind you that there are 3 points. What does it mean by the 3 points here? First, in your mind, you already know that what is an open circuit test curves for a given generators? Okay. So this is the general curves of the field currents internal generator voltage for a given generators. For self-excited generator, the excitation currents, field currents RF, comes from the terminal voltage. Okay, so the terminal voltage depends on the internal generator voltage. And to the beginning, when the generators is not started, the generated voltage be 0. The terminal voltage also be 0. As a result, we have no source for the excitation currents. Even you're making the so you're making the rotors be rotated here, but because the field current terminal voltage be 0, the field current be 0, therefore the excitations be 0, the generated voltage be 0. Okay. It is the field current that to produce magnetic field that cutting the rotors so that we have generated voltage. That's the basic issues. But if the generator itself has no excitation, not started, there is no terminal voltage. There is no excitation currents. There is no generations, and so on. You cannot start it. However, for most of the IR cold coilers, okay, here, as we mentioned that, okay, for the excitation, right, coilus, the field coilus, it usually with the core, right, materials. That the core materials is the iron core materials. For most iron core, okay, called coilus, once it is magnetized, that means once you apply the current there, then there are magnetic field produced there. So the produced magnetic field, okay, even the current becomes zero, there is residual, right? So we said residual, right? So there is a residual flux remains, okay, for a wire. Okay, so how long the residual flux remains there depends on how strong you magnetize of it. Okay, so this is the residual flux. Residual flux. Okay, what does it mean? So if we have a coilus with the core materials there, we apply a current to it, then there is magnetic field produced. Then we cut the currents. The magnetic field not so strong, but there are some magnetic field remains in the core materials for long times. Okay, maybe 1 years, half years. Okay, then the magnetic field gradually decreases, disappears. But within a certain times, the magnetic field maintains at certain values of it. Okay, so in such a way, even the magnetic field is weak, but there is rotations. Then there is the coilus cutting the residual flux. So for a given generators, if there is residual magnetic flux there, once the motors is driven, once there is a engine drives the movers, there is rotations against the residual flux. There is flux cutting movements. There is induced voltage internally. So this induced voltage probably be smaller, but always be there. So when there is movements, there is generations. So with this small generation, we have a small internal voltage. We have small terminal voltage. Therefore, we have a small field currents. These small field currents produce extra magnetic field plus the residual flux, making the generated voltage be larger and the field current be larger and generation be larger, field current be larger. So as a result, when there is a residual flux, there will have right, once there is rotation, although the field current be zero, there will have internal generations. So as a result, the internal generation field current curves becomes things like this. Here, okay, so we have, right, once there is rotation, That's the meaning of it. So with residual flux, once the rotor moves, there will be a small internal generator voltage generated. That's why we say that for the self-excitation generators, residual flux is necessary. It's necessary. Okay. As I showed here, so the self-excitation, the general case, the excitation curve is the blue one here. If there is residual flux existing there, then the excitation curves will be like the red curve will draw here. Okay, that's the meaning of it. So once there is a rotation, there will have a starting internal generated voltage because the residual flux there. So successful self-excitation of a system requires the residual flux. Okay, so this is one thing that we should understand. Okay, so why we need residual flux? Because it is a self-excitation generator which requires a starting flux, that for the starting generation. Otherwise, no generators cannot be started at all. The second point is that the non-linearities. Look at it here. So the curve actually already show here is non-linearities here. So why we say non-linearities? Because that the excitation curves so this is the first point that what does it mean by the residual? Okay. The second point is that the terminal voltage, the field currents equal to field voltage, equal to field voltage over the field resistance, because it is a self-excitation. The field currents equal to the field voltage over the field resistance, because it is self-excitation. So the field current voltage always proportional or equal to the terminal voltage. Here, root mean square values. Okay. We say the field currents equal to the terminal voltage. Okay. So because the terminal voltage is the internal generated voltage, minus the armature currents times the armature impedance here over the field current. field right circuit resistance, which generally you has a constant resistance with adjustable resistance. Okay, here. So because it is a self-excitations, you can imagine, okay, here, although okay, we not draw here, but okay, based on your understanding about self-excitation. So look at here. So the field currents, that is the field voltage over the field resistance. Because it's a self-excitation, so we get the field voltage from the terminal voltage. Okay, and the field resistance comes from one, okay, some resistance related to the field coilers, the other one okay, related to the additional resistance. Okay, so in such a way, and the terminal voltage is the internal generated voltage VA. Okay, so we usually using the EA. Oh, sorry, mistake. Terminal. Okay, so the field currents, that is the field voltage over the field resistance. Okay, so and because of the self-excitation, so the field current, field voltage, for your easy understanding, we write down here that is the okay, terminal voltage, okay, with the okay, field resistance, okay, which furthermore is the internal generated voltage minus the field currents, sorry, the armature currents times the armature impedance, synchronous impedance, over the field resistance. Okay, this is a straight line. Okay. Okay, so because it is a self-excitations, so when the okay, according to this right, okay, formulas we show here that the EA to the RF, okay, from here EA to the RF is a right straight line. Am I right? Okay, you can see that EA. Look at here, that means the EA equal to the field current RF times the field circuit resistance RF plus the armature voltage drops, right? So if it is open, right? If it is open, look at here, RA, if it is open, the EA related to the field currents, why? This is straight line, this straight line. Okay, straight line. If the field currents, right, bigger than EA, you're bigger, field current smaller, and be smaller. On the other side, okay. So the third point is that, okay, from the generation itself, the internal generated voltage proportional to the field currents, while a coefficient chi and the rotation speed omega r. So this is a nonlinear curve. So from the excitation itself, it is a nonlinear curve relationship between the field currents and the internal generated voltage. From the excitation, self-excitation, okay, circuit, that the internal generated voltage related to the field currents, while the field circuit RF is like this. This is a straight line. Okay, this is a straight line. So for the same parameters, it is right related to the field currents. One, straight line. Two, a nonlinear curve. How making the solutions be unified? That is the cross of these two when they are, okay, stabilized. Okay, so as a result, okay, this is the, okay, straight line. Okay, so from the excitation branch, from the excitation circuit, one can find that, okay, the internal generated voltage related to the field current RF, right? Okay, in a straight line. Okay, straight line. While that from the, okay, excitation branch itself, that's the internal generated voltage related to the field currents, okay, via this, right, excitation curves, red one. So the stabilized points will be like this. So this is the solutions. Okay, so when the field current is smaller, so the generated voltage will be smaller. Okay, their excitations will, right, will fluctuate between these two one. So their excitations will follow such a way. This is the excitation process. So when you have the internal generated voltage, this internal generated voltage comes to the straight line to get the field current RF. With this field current RF, you have excitation like this. This right generated voltage. This generated voltage come to the straight line curves to giving the field currents RF. The field current RF in turn to generate a voltage given on the red line. That red line generated voltage, EA come to the these curves to giving the field currents. As a result, you stabilize at these points. That's the non-linearities. So non-linearity is necessary for the self-excited generator. Otherwise, the excitation cannot be successful. This is the second point of the non-linearities I explained here in detail. The third one is easy to understand because the field current regulators, that means, look at it here. So these excitations based on the rating voltage require the terminal rating voltage is different. You require different field currents, So you may have different excitation curves. For example, if you have excitation curves like this, not successful. Because you can determine the RF with different values, so that the relationship we show here, the second point we show here, has different slope. So some slopes, the generator cannot start properly. Some slopes, the generator can start it, but cannot stabilize at all. They waiting a very, very long time to stabilize. So we have voltage, field currents, RF regulations. So we must to control the RF so that the field current IA be reasonably created, so that the internal generated voltage, finally the terminal voltage, balanced and reasonable design points. So here is my explanations for the 3 points I listed here, based on your knowledge learned. So for successful self-excitation, residual flux, non-linearities of the excitation curve, the field current control or regulation are necessary. This is the conditions. Now, we're looking at the flow chart here to see how does the self-excited voltage control unit works in practice. Now, suppose this is the armature outputs. Generally, we have the current, okay? We have the current feedback unit. So we have the control feedback unit, okay? We use this one to monitor the output voltage. Okay, monitor output voltage. And to get powers for the excitations. Okay, unit. So from here we get the, when you have generated currents, we can gauge the generated voltage here, that feedback, a power unit here, a power unit. And also at the output terminals, we have the current monitor systems. That is current CT, because generator output current will be very big, current CT. So which monitor loading current levels. And meanwhile, we have one of the sensors monitor the terminal output voltage. So we have voltage here. We have the terminal voltage be monitored here. We have the armature current monitored here. So, monitor the terminal voltage, monitor the terminal currents. Then we have the reference inputs, reference. We have reference signal here to see whether the terminal voltage is too small and whether the armature current too big, increased or small. So this is the reference signals. Then we come to a voltage control unit. This is the voltage control unit. Voltage control unit. And here we also gauge the powers for the voltage control unit. We have the powers. Because this is powers to control unit logic systems. We have logic systems here. So based on the reference terminal voltage and the current signals, then we have a logic outputs here. So based on this reference inputs, that we can make judgment whether the field current should be increased or decreased. So with these orders to the power unit, power unit. So the power unit determine the field currents. So if necessary, the field current increase, or decreases. But all the energies comes from the terminals, terminals. So control field units, field units control powers comes from the terminal itself. all the powers generate, okay, at the terminals, okay, at the armature terminals, okay, powers. So for the exciters, rectifiers, in major rotors and major right stators, we have explained it previously, no longer repeated here. But here we just explain you how the self-excited voltage control unit works. Okay, so the 2 points. The first point is that we monitor the terminal output voltage currents so that we get reference inputs. Based on these reference inputs, we get orders on how to increase or decrease the field currents, how much it should be. And during this process, we get the powers from the terminal outputs, okay, to the exciter power units and also to the voltage control units. Okay, so this is for the self-excited generators. We should understanding what is the necessary conditions for successful excitations of the generators. I listed here 3 points here. The second one, how does the self-excited voltage regulation systems works? I'll explain to you in details of it. Because, we suppose that you have already in your mind in the relationship between the terminal voltage and the internal generator voltage, the generations, and also the principles of the generators. So here we just simply show you a flow chart here. So to introduce to you the principles of the self-excited voltage control units, and also explain to you the necessary conditions for successful excitations of the generators. Okay. So hope you have a good understanding on how the self-excited generators works. Okay. So the second type is, of course, the separated excited voltage control unit. Of course, in that case, the machine, the generator itself is self-excited. It is separated excited. Okay. Here we have simple drawings of the separate excited voltage control unit systems. So here that means obviously that the exciters powers comes from external source. Of course, we still need to monitor the terminal voltage and currents. Here, so we have the terminal voltage A, V terminals, and we have a reference current. Then we got the reference reference signals to the so-called voltage control unit. In the voltage control unit, the powers comes from external powers. This is a separate power unit. Separate power. So the voltage control unit that by the separate power unit, So which also provide the powers from to the exciters. That with the reference signals, they can increase the powers to the exciters or decrease the powers to the exciters. Here, so this is you can see as a separate power unit, because here we have the permanent magnet. Permanent magnet. here we can use a permanent magnet to produce the field, so that there is a right rotations. There will have right powers generated here. These powers can be used as the right voltage control unit powers. Okay. So this powers is not comes from the generator itself. Okay, or generator cells. So these powers then can be used to for the exciters. Also, you can use batteries here. It doesn't matter. Anyway, this is a typical right. Separate excite generators. So we have the separate powers here. So these powers supply the powers to the voltage control unit. Also supply power to the exciters here. So based on the terminal output voltage currents, so with some of the solid state right control units, so we can increase or decrease the field currents which input to the exciters, so that we can control the internal generated voltage on the main stators. So it is the main stators, the generated voltage that to control the terminal voltage. Okay. So this is self-excited voltage control unit working principles, which are very similar to that of the self-excited, but the unit the difference is that the power unit for the exciter and for the voltage control unit is separate from the generator itself. The previous one comes from the generator armature itself. This one, the power unit for the voltage control unit and the exciters is separate from the generator armatures. Okay. So these are two types of the voltage control unit, or the two types of the AC synchronous generators. Okay, so far we almost finished talking about the principles, equivalent circuit, testings, and control of the generators. The things left, of course, is one that is the power flows inside generators, which we need in details to talk to you in details. Take a few minutes. Okay, so examples which actually already talked in the tutorial sessions. Okay. Now, here we have one slide showing you the difference of the performance between the two types of the generators. One, the separated excited generator, and two, the self-excited generators. Suppose it is a self-excited generator, then the for self-excited one, the field voltage comes from the terminal voltage. Here, the terminal voltage. Okay. If the terminal equal the field terminal voltage, which is the terminal currents times the load, equal to 0. Then the field currents equal to the field voltage over the if also be 0. That's the point of it. For self-excited gate generators, as I explained to you, that the field voltage comes from the terminal voltage. So in the root mean square values for DC and AC, that the field voltage which is equal to the terminal voltage because it is parallel to the terminals. If the terminal voltage due to the short circuit, the terminal voltage is the terminal current, okay, I times the loading times the loading. If the terminals is short circuit, that means the loading impedance is 0. Okay. So then, if the loading impedance be 0, the terminal voltage be 0, and the field current will be 0, and the internal generated voltage will be 0, and okay, terminal current will be 0. That's the meaning of it. Okay, so I write down a short sentence here. So for self-excited one, so the field currents, that field voltage, that is the terminal voltage. Now, so this is the case. Now, if the terminals is short circuit, the terminal voltage, that is the terminal current times the impedance, loading impedance. So when short circuit, that loading impedance be 0, the terminal voltage be 0. Then if the terminal voltage be 0, field voltage be 0, field current be 0. If the field current be 0, then the internal generated voltage will be 0, and the terminal voltage be 0, and therefore the terminal current will be 0. That's okay. The points here. Okay, that's the points here. For short circuit current of generator under steady state conditions can be calculated as okay follows. For self-excited one, the short circuit current will be okay come down to the 0. Okay, come down to 0. So this is the advantage of the self-excited generator. Okay, so this is the advantage, right? So of the self-excited generator in abnormal conditions. That means in practice, if this is a self-excited generator, if there is an overloading occurred or short circuit occurred, then the generator will automatically stop. Right? okay, stably, right, they will get done, okay, as die out. So self-protective. Okay. Now, for separate excited generator, okay, then the case will be, right, different. Separated one, okay, the V, okay, A equal, sorry, EA equal to, okay, okay. So if RF no change and terminal short circuit, then the terminal currents will equal to the, okay, terminal currents, because the terminal impedance be, okay, the synchronous impedance plus the short circuit impedance. Okay. For separate excited generators, the internal generated voltage, which depends on the field current and rotation speed. So the field currents, that is, comes to the field voltage over the field, right, circuit resistance. If the field currents no change and the terminal short circuit, then the terminal currents, that is the internal generated voltage, over the armature synchronous impedance plus the short circuit path impedance. Generally, the short circuit path impedance is very small. The internal, okay, impedance of the armature is also relatively small. So this current will be very large. Okay. Okay. So for the, right, separate excited generator, so in the short circuit cases, the short circuit current will be very large. So this may damage the generator itself. Now you understand that in practice, most of the big generator adopts the self-excited mode rather than the separate excited one. Because the self-excited generator has the advantage that in the abnormal conditions, the generator itself self-protected. While that the right, separate excited generator, in the conditions of the short circuit, the big, right, short circuit currents may destroy the machine itself. Now you should understand, okay, why we have such statements here. This is the right explanations about the, okay, self and separate excited machines in the conditions of the short circuit or overloading conditions. You should know how to explain to the others that what is the advantage and disadvantage of these two types of the generator in abnormal conditions. The last point is that the internal power flows of the generator with the knowledge about the transformer and induction motors. So the power flows inside the generators is not difficult for you to understand or to follow. Okay. Now, for in comparison with the motors, the generator's input powers is the mechanical powers. Usually, there is a so-called engine that drive the movers or the rotors of the generator. The input powers, mechanical powers, can be described using the torque applied here, T applied, and the the mover speed, omega n here. So this is the mechanical input powers. Inside the generator, due to the field currents, there is the magnetic field generated there. This magnetic field, not all of this generated magnetic field taking functions there. Some of it, due to the structures, due to the whatever conditions, and there are parts of the right field that not to generate voltage, participate in the generations of voltage. So that's the kind of the energy losses. Okay. The strain losses be there. And also we have the friction and the windage losses because the mover is moving surrounding axis. So the axis may have some bearings, whatever. So all these mechanical parts has frictions between each others. And also, because we are on the earth, in the air, or even in the waters, or in whatever mediums. So the rotation of the shaft, the movers, against the surrounding mediums has the so-called windage losses. Friction and windage losses. The third one, of course, we have the core losses. Once there is generated voltage and with generated currents, there will have the core losses. Because when there is generated voltage across the coils, then there is magnetic field right inside the coils. If the coils of the core material itself is conductive one. There are small currents there. So the ring currents, the eddy currents, and hysteresis losses, eddy losses occurs inside the core materials, that is core losses. The energy left, is the pure energies that for the inductions. So here, the pure inductions is the voltage generated. So from the electric side, the energy that is the internal generated voltage, okay, times armature currents. This is the right. This is the generated voltage times the cosine okay. So the mechanical input powers, that is the induced torque, which is the pure torques, okay, to overcome the internal generations, okay, due to the interactions between the rotors and armature currents, okay, and mover speed. So this is the real powers. So mechanical powers is the real power only. Okay, real powers. So for the electrical side, the real powers is the armature generated voltage, the armature currents, the overall power factors looking from the armature outside. Okay, armature's outside. That's the meaning of it. Okay, that's the powers. And on the armature side, of course, we have the copper losses. Okay, so the armature currents, the armature resistance, the copper losses. Then the electric output powers, which is terminal 9 voltage, terminal 9 current, the loading power factors, the 3-phase √3, the output powers. So now you're understanding the relationship between the input mechanical powers, output electric powers. Theoretically, if the electric powers outputs be 0, that means the loading current be 0. If the loading current be 0, then you have generated voltage be here, but you have no energy outputs. And the air gap, right, induced, so the mechanical energy also be 0. The torque will be 0. You have the rotation here. You have no torques, so no force there. So the input energy is just the losses to overcome the friction advantage and the core losses. No copper losses here. So when the secondary is opened, the input powers, mechanical powers, is just the friction weighted strain and core losses. So open circuit test can give the core losses, mechanical losses, strain losses of generators. In practice, we can do the open circuit test like this, so that we can got the generators open circuit losses. The copper losses, of course, depends on loading levels. If the loading level higher, copper loss is bigger. Loading level smaller, copper loss is smaller. Because that here we do not write showing you the right open circuit test with the mechanical input powers. We not show you that, but you should understanding that when the mechanical input powers rotation speed keeps the constant, then you to overcome the friction advantage and core losses, you have applied a small torques. This small torques is used to overcome the friction and core losses here. As a result, that the input powers is the mechanical applied torque times the mechanical movement speed of the mover. And the air gap energy, which is the input mechanical powers minus the friction and windage losses minus the core losses, if strain losses there minus strain losses. That's conversion energy. So here is the conversion energies. Conversion energies. Okay. So for the stator copper losses for three-phase, the stator resistance, stator currents, 3 times of it for three-phase. Okay. For the electric output powers, one can measure it as the 9 voltage, 9 currents, and power factor loadings. Okay. And the electrical output powers related to the internal converted energy, while the stator copper losses, stator copper losses. So anyway, here showing you the input mechanical powers and output electrical powers, their logic relationships inside. And also the efficiencies, the definition of the efficiency is the output electrical powers over the input mechanical powers. Note, in electricity, the voltage represents the possible potential difference that to provide current to the loading, but the powers represented by the currents. No currents, no powers. In mechanical one, the movements just represent the movements with no torques. There's no energies. Torque that related to the force. No force on the movements. No power on the movements. That's also the Newton's law, right? If you have no force applied to object, the object keeps their movements as zero. Movements as zero. So this is the power losses inside the generators. We have a very simple flow flow chart here because we suppose you have the knowledge of the power flows for the motors, power flows for the transformers. We not necessarily repeat some of the similar issues for all the machines. So so this is the end of the synchronous generators. Starting from the next lectures, we will talk on the DC machines, including both the DC motors and DC generators. For the DC motors, we have the synchronous DC motors and synchronous DC motors. For the DC generators, and the DC synchronous and the synchronous DC generators. We also have different kind of the excitation mode of the generator and the motors. The contents is very colorful. We have many contents there, but because the principles we already have learned in detail for the induction motor and generator. So in the DC motors, we goes slightly faster than what we did for the motor and the generator. So that's the end of today's lecture. If you still have some questions or inquiries on the motors and generators, you can use in the following few minutes to chat with me, or you can write to me via the emails later on. Okay, thank you for attending today's lecture.